Okay, so I need to give you a whole bunch more words going with polynomials. Okay, so first I want to give you the last thing first. So I want to give you standard form for a polynomial. Okay? So standard form feels a lot like, I hope in your mind, the thing you do with quadratics to rearrange them before you cram them in the quadratic formula.
Ax squared plus bx.
Perfect. So for a quadratic, right, I'm kind of thinking ax squared plus bx plus c. Okay, so on this, I'm just going to say, all right, I don't know how big this thing is. So I'm going to say, I'm going to call this p of x, right? I'm going to say, okay, well, I don't even know the degree, so I'm just going to start with the highest it gets. So I'm going to do an, that's like the a, right? X to the n. You guys cool with this? Then I'm going to add, and what? What's the power going to do?
-1.
Yeah, I'm going to go down by 1, right? So I'm going to do whatever the number is on that term, x to the n minus 1, plus an minus 2, x to the n minus 2. And then we're going to do and so forth, right?
Until you get to x.
Until I get to x, where I'll have, what's the number on x going to be called? So I've been pairing an with x to the n, right? And an minus 1 with x to the n minus 1. So with x to the first power, I'm going to pair
1.
a1.
What does the 1 mean?
So the 1 is just saying which term of x that goes with. Right? So this is just saying, this is the number that goes with x to the first power. Cool? In the same way here that your a, b, and c went with x to the zeros, x's, and x squareds, we're going to do the same thing counting down. I'm just not sure how many there are, so I didn't want to use the alphabet because there might be 30. That's cool. What's my last term going to be?
Whole number.
Yeah, it's just going to be a number, right? So I'm going to call that a0 because that's with x to the zeros. You guys with me? So standard form here is that thing there.
A to the 0, or that whole thing.
The whole thing. All of it.
Increasing the hours for left and right.
Yep. So we're just starting with the highest power, we're writing the number that goes with that, then we're adding, and we're going to write the number that goes with the next one, and so on and so forth till we get to the bottom. And we know this will stop, right? Because there's only finitely many because it's a polynomial. Okay? So that's our standard form. Let me see. You guys said something about coefficients, right? What are the coefficients?
That's the number before the variable thing.
Yeah, that's the a's. Cool. So all of the a_n's are coefficients.
And degree is the highest power it goes to.
Degree on this guy is the highest power, which in this case is
N.
n. Okay. Zeros we'll talk about in a second. What are the terms?
The things separated by pluses and minuses.
Yeah, good. The things that you're adding together. So I'd call that aj x to the j's, right? Cool that? So any of the things you're adding together. So which one's the constant term?
X.
No, close. X is a variable, right? Which one doesn't vary?
A to 0.
Yeah, the one with no variable doesn't vary. So the constant term is a sub 0. What's the leading term?
A. Just A.
The term out front, right? It's the term in the lead. So that's an x to the n.
So that's just the highest
Yeah, so that's the highest power of x present and also its coefficient, which brings us to leading coefficient, which is
A to n, or A n?
a sub n. Perfect.
So then,
Cool. So please note that you guys know some stuff. The stuff you know is this thing here, the constant term, corresponds to what? So if you knew what the graph of the rest of this crap looked like,
It's a vertical shift.
that thing is something about a vertical shift, right? You guys see that?
Can you say it again?
So we could think about that as a vertical shift on the rest of this.
oh yeah.
You guys see that? So sometimes that thing's very convenient. Not always. Sometimes I have to like complete the square to figure out what the rest of this shit looks like. But sometimes that thing is just straight up the vertical shift, which can be very convenient. Even when it's not the vertical shift, what is it?
Y-intercept.
Good, perfect. It is always the y-intercept. Just cool that. Okay. Now, what else do I know? The leading coefficient. What are you going to think about that thing?
Compression. Or
Yeah, that's going to have something to do with your compression, right? Wait, this way?
Over.
Yeah, that's going to be this way. That's going to be your vertical compression or stretch, and maybe your flip. Okay? So, when you look at that, I want you to think vertical compression things. Definitely always look for a flip. That is always look at the leading coefficient to look for the flip.
The leading term be labeled as the skeleton of the function in this?
Yeah, that's actually a fair point. This leading term, this will give you a pretty good idea if you like mega zoom out. You guys see that? So like if you know what this guy does, if you super zoom out, that's basically what you're going to be looking at here. So like if you have an ax squared plus bx plus c, right? That's going to look like a parabola. And if I zoom far enough out, it's going to look like ax squared. You guys see that? Because this is going to be horizontal and vertical shifty business. But if I zoom far enough out, that stuff's going to kind of disappear. You guys with me on that? If I have a cubic, cubics could look like this. You know, this is like a3x cubed plus a2x squared plus yada yada, right? Say yada yada two things. a1x plus a0, right? But if I super zoom out on this, I'm going to see a cubic, basically. You guys with me on that? What can you tell about this cubic right now, specifically about A3?
Positive.
Yeah, right now you know this thing's positive because it didn't get a vertical flip, right? So I know that the A3 is positive.
Who knows, it could have gotten both a vertical and a horizontal flip, it's the same.
Yeah.
Does it even matter?
If I write it this way, the A3 will take into account both of those. And so it'll still be positive. You guys cool with that?
So if it's negative, it doesn't matter which one it does?
Yeah.
That's weird.
Yeah. I would think about it in terms of a vertical, because that's going to be easiest for your kind of mega zoom out behavior.
Just
If you think about it as horizontal, it's going to be a little funny. But yeah, with polynomials, it actually doesn't matter. The reason it doesn't matter is that the degree is going to tell you something about kind of long run behavior. the degree is going to tell you whether it looks roughly like this or roughly like this. You guys see that? Which ones does this go with?
Squared.
This goes with x squared and also with
4 and 6.
and also with 4 and 6 and 8 and yeah. So this one says even ends. Yeah, because kind of the mega zoom out looks like an even function. Okay, see that? These don't have to be even or odd functions, right? Because once you add those other terms in there, they might not work quite right. But at least if you mega zoom out, it looks even. If you mega zoom out, this thing looks odd, right? And that's actually why we call them even and odd. Right, because those labels didn't make much sense for sine and cosine, but they make hella sense for polynomials. You guys cool with this? Basically. Okay, I didn't talk about zeros.
Oh, I know, those are solutions to the thing, right?
Yeah, zeros are the solutions to p of x equals 0. The important thing for this is how many of them can there be?
With an even degree, it could be 0. With an odd degree, it has to be at least 1.
Cool, that's a good observation. The degree is odd, right? This thing. Something looking like that's going to cross the x-axis someplace. You guys see that? And that's really what I'm looking for here, is I'm looking for x-intercepts. This guy doesn't have to. That's good to know. I should also know that there are at most
N solutions.
n. Okay, that's a thing called the fundamental theorem of algebra, which is super cool.
Who made that? Wasn't it?
Good question. Not actually sure. That one goes back a ways. There's a bunch of different proofs of this thing, but basically it boils down to a polynomial of degree n can have at most n solutions, and if you go look at the complex numbers, it does have n solutions. Cool. We'll talk some more about what exactly that means later, but I want to play with catapults. Cool? Sorry?